Thank you very much. So, okay, so this is work that some of it is things that we have known for a long time, and some of it is things that we still don't understand very well. So, so let me tell you how you go from Darwinian dynamics to thermodynamics, something that is by no means obvious. So what is Darwinian dynamics? You have something that is could be your genome or could be some switches, some chemical switches inside a cell, which are switching randomly or mutating randomly. And this produces an organism that is more or less fit according to what the effects of this are. And being fit means being able to make many children per unit time and, if possible, not dying. So, selection acts, of course, on the results. So there is no force, that Lamarckian force, that makes you mutate. You mutate randomly, and then selection will penalize you or reward you. So let me just, to fix the context, suppose that you have, for example, cells in a chemostat. A chemostat is a thing, an apparatus that was invented by Szilard, and it's not so surprising because he was a physicist, in order to keep constant the number of cells in this case. So you flush them in a way, in a time-dependent way, so that you keep the number constant. The idea being that you want to attack your conceptual problems one at a time, and that this would be a typical physicist simplification. So this is a very much an ideology of a physicist. So we shall assume that somehow there is an external agent that keeps the population constant. So if you are being very successful, this will necessarily be at the expense of somebody else, because the total has to be kept constant. So, okay, so let me consider the simplest model I can think of, and then we will see how selection comes about, and then how a notion of thermodynamics appears very surprisingly. So imagine you have, this is known as the house of cards model. It's called house of cards because you have several types, types meaning, for example, genotypes, and you mutate randomly. And each mutation can take you from anywhere to anywhere else. It's completely random. This is a simplification, of course. And in each of these types, you have a fitness, which is, I denote lambda throughout. This is the amount of children you make per unit time. And you have a mutation rate that can be the same for all or not. So whenever you have a particular type, you will last on average for a certain time. When you have children, your children are in the same type. They inherit the same mutation rate and everything. And Mr. Kingman called it house of cards because when you jump away from a phenotype or a genotype or whatever a type is, you lose completely everything you gained up to there, and you go randomly to somewhere else, which can be very bad or very good, or it's completely random. So it all collapses as a house of cards. Of course, this is not very realistic, but okay. So let us assume, now there is an element of random energy model. This is why Derrida's name is there. You have to choose some distribution for the fitnesses, and we choose them as being 2 to the n types, and just random Gaussian. So it's a parabola here because this is the log of the fitness. And so you assume that they are distributed according to Gaussian, which you choose once and forever. So things will evolve in this way, and you have a population of m individuals kept constant by your chemostat, and you want to wonder how is going to this system evolve. So you have the numbers of occupation of each type, which evolve in time on average, and you would like to know things about this. So this is a dynamics of a distribution. Now, this dynamics doesn't satisfy any theorem like classical mechanics, has of course no detailed balance, so has no notion of temperature or equipartition or whatever. And hence, you cannot do what you do in chapter 1 of all stat mech books, where you go from classical mechanics to statistical mechanics just by saying, let me assume that an energy shell is explored uniformly. This step allows you to just don't do dynamics and study the landscape by itself. This is what makes it possible that you do an entire course of StatMech without even ever studying dynamics. Here you cannot do anything of the sort because you have no guiding principle. Of this dynamics you know very little. So you have no inequalities, no second principle like things, no arrows of time in principle. All in all, you have no thermodynamic thinking. So this is something that is a bad state of affairs for a physicist. Well, the system ages, I'm going to come back to this, when you consider this system undergoing this dynamics, it starts to evolve, but it evolves slower and slower. This I'm going to come back to very often, so I'll just pass. And so what does this population do? So you can divide the evolution of this population in, let's say, 4 different epochs. At the beginning, you have a uniform, you have a smooth density of probability of population over the different fitnesses, and this evolves, and you can treat everything as if the number of individuals you're considering would be infinity. So you have a density of having a certain fitness, and this fitness evolves with time. This is a regime where everything is easy to calculate, or relatively easy to calculate, but unfortunately this regime doesn't last very long, because what happens after a short time, if your population is finite, what happens is that after some time, what you find is that this is, for example, the population of all the of where every single individual is. L is just one over the mutation time minus the fitness. You see, at the beginning you have like a continuous cloud that is evolving, but you see that after a relatively short time, all the population, or a big fraction of the population, is getting condensated into only one type in this model. And here you have 3 of them, but as time passes, this becomes more and more rare, and at the end of the day, you end up by having jumps between essentially all of the population condensated into one type. This is a finite size effect, but unfortunately, this finite size effect is logarithmic in the number of individuals you have. So very soon, the approximation of treating this cloud as some sort of uniform approximation, the quasi-species approximation also called, is no longer going to work. And what you have is a regime of takeovers of the population, essentially all colonizing one type. And then just turning over, flipping to a new population type, and so on. So here you have, for example, in terms of the time scale for this model and in terms of the fitness, this is the population at a long time. Almost all of it is in a place with very high fitness and very high time scale. And just there are very few individuals that are not in one single type. Okay, so this is a natural consequence of the Darwinian evolution plus the distribution I chose for the system. Yeah, please. Sorry.
Is fitness simply reproduction frequency?
Yes, but in fact, the actual important parameter is fitness minus the mutation rate. Yeah, that's the one that is like this. Yes. Okay, so let me consider now the hops, and this is going to be the important part. Let us consider the dynamics of once we get to this regime, which is pretty soon, we shall consider these hops between populations that are all in the same type, and they are fixated, so they are predominant, vastly predominant, and they are jumping from one type to another. In this particular case, we chose some very wide distribution, although not with fat tails, but this was another model. In fact, from here onwards, it's going to be only one tau, and that's going to be all. So, the problem now of the fitness of a population that is entirely in one type is the problem, is the same as the following problem. You have a desert, a very bad region, and you have birds, and they would like to live in this happy island where they make lots of kids. And it suffices that one of them migrates to the happy island. It will make a lot of kids because we are keeping with the chemostat the total number constant. Very soon we will end in a situation where the whole population will be in the happy island because of the constancy of the total, and the desert will be empty. But this is exactly the same situation as why national parks are not very useful to avoid extinction. Just randomly, birds have a slight probability, a tiny probability of, wanting to fly to this desert place. And you have a chance that is non-zero of this extinction, this population becoming randomly extinct. Even if the happy island is very happy, you have a slight chance that this might happen. And once it's happened, and if there is no future immigration, you're dead. And this is exactly what happens with national parks. You have the jaguar who's happy, but once a jaguar leaves, he dies, and then there's no other jaguar that will come in. And you wait for sufficiently long. If the mass of the national park is not infinite, you will have no jaguars. So, okay. So this kind of situation you can calculate analytically, and it turns out that if you're going from an unhappy place to a happy place, and the two fitnesses are lambda I and lambda j, turns out that the probability that the entire colony of, in this case, cells is in the type I, it's going to j, can be calculated, and it gives this number. So that for large population size, you can approximate it this way. So an improvement, so you are in an unhappy place and your first cell emigrates to a happy place, boom, with probability essentially 1, the entire population will flip to the new place. But you can also get a random extinction that going from the happy to the unhappy place, the whole thing extinguishes with this probability. So it's exponential in the number of elements you have. Of course, if you colonize a happy island with 2 birds, the chances that it will get empty are much higher than if it's a happy island, that even if it's a happy island, that if you have 2 million birds. So you have this rule. This is just an independent calculation done with the Darwinian, let's say, the selection mechanism. And notice now what we have got. This is exactly a Monte Carlo rule to flip between, to equilibrate. It's exactly like the program you use in the computer when you want to get the Gibbs measure, when you want to thermalize a system to a temperature that is 1 over m. So it is built so that it has detailed balance. It's more or less like the Glauber rule. This is the Monte Carlo rule, but it's the same. The idea is that this will lead to an equilibration with, as an energy, the log of the fitness, and as a temperature, an inverse temperature, the size of the system. Notice that there was no conceptual reason why temperature should enter here. It's just a consequence of just having done the calculation. So all in all, we have done the following steps. We observed the fact that in this system, at least, the population got concentrated, fixated in only one type, and then it did essentially flips between the entire population, flipped between different types. And then a meta-dynamics of these types, if you want, is a dynamics that is thermal and whose temperature is 1 over the total population you have. So this is a surprise. Like, one cannot give a conceptual reason. There is no, it's just the way it happens. So the equilibrium distribution, you're guaranteed, because this is detailed balance, that is going to be this, because it's lambda I to the, which is, sorry, here there's a log, because what plays the role of energy is the log of lambda. Okay, so for example, you all know that when you have a population bottleneck, this accelerates mutations because a few very rare guys can have the chance to make lots of kids, and then you have something very strange propagating in a big population if it comes back. Well, a bottleneck in this language, because the inverse temperature is the size of the colony, the bottleneck is like a spike in temperature. It's an m going down, which means that 1 over m goes up, and this is a spike in temperature. And this is exactly what you would expect of a system that is evolving with temperature in a rough landscape. When you anneal, what you do is spikes in temperature, which accelerates the motion. So all this looks great, and the whole thing looks great because now we see some thermodynamics getting into a problem of which we had no generic handle. Okay, so we can make a model, for example, a meta model now. Forget about all the details we said at the beginning, and now let us make a meta model where we propose that we have a colony which comprises everybody that is jumping as a whole. This is a kind of condensation of the whole, a schematization of the process I mentioned before, and you make it jump with this probability, which is the one that it's true for an entire colony. So by the time you get this takeovers regime where the whole thing is fixated in one type and it moves to another type, it moves with this dynamics, and you can invent this model, which is sort of works in the same way for long times. And then if you have small m, what happens is that, like, because this is playing the role of inverse temperature, equilibration happens when the derivative of the log of the number of states is equal to the inverse temperature. So all in all, if you draw a line whose gradient is m, if m is small, this is the place where the system, if it evolves, it will end up by equilibrate here. So there is a notion of equilibration. What happens when you're equilibrated? It means that you would like to have larger fitnesses, but every now and then you make a jump to lower fitnesses because they are overwhelmingly more. The states, remember that this is an exponential, it's a log of the probability. So, so this balance happens for this point, and you get equilibration here. And if m is sufficiently large, on the contrary, what you get is that the system keeps on going down until it meets the last state, the best of the best, and there it freezes. So, okay, this is what the meta model says, and it's a representation of what the true original model is going to do for any m at very long times. So it looks great. You see, you have something that this was very well known since long ago. It's called the Muller ratchet. Is the idea that if you make bad mutations, because there are so many more bad things to mutate into than good things, there comes a moment where, by entropic reasons, simply by the number of possibilities you have, you are going to be doomed to get worse. But now we understand that this argument is just the usual stat-mech, the usual thermodynamic argument for thermal equilibrium. Why doesn't a thing go down to its lower energy? Because, just a glass of water, because when it moves, it has many possibilities of getting hotter and less possibilities of getting colder. And this balance between the number of possibilities and the fact that you want to be colder, this balance between energy and entropy, is what gives you equilibrium. So here you would have exactly this same thing. And whether you continue to improve or you deteriorate depends on this transition temperature, let's say, the freezing temperature. And all this seems very beautiful, and we're all very happy, and it looks like thermodynamics has entered by the big door to treat this kind of problem. So all this seems fantastic, and you could do lots of things, and you can do entropy fluctuation. This was discovered, maybe with slightly different words, but essentially discovered 10 years ago by, as far as I know, these two, Lessig and Berg. Maybe there's something previous, I don't know. So, question you ask is, why isn't everybody working on this? I mean, if you're going to reduce the whole population dynamics to statistical mechanics, it looks like everybody should, every physicist who's interested in this should be working on this. And well, okay, so let me say at least two reasons why not everybody's working on this. First of all, in order to have this clustering into one type, which I used to be able to say there was detailed balance, I need that there is a very big separation of timescales. All the birds went into the same island, And in that time, they didn't go to yet another island. They filled in the island, and then they waited there for some time, and they had the time to go and inspect a third island, and so on. So you need this separation of time scale, which in our model exists, but in general it does not. And in general it does not, and when it does not, the whole detail balance argument collapses, and you no longer have the notion of temperature. And because we know that it is not generically true that every single possible individual is in exactly the same type until they all flip into something else, this cannot be possibly true. Number two is that, even perhaps worse, that even if you are in contact with a nice, decent thermal bath that satisfies detail balance, the landscape is too complicated. So, and when the landscape is too complicated, you simply do not have the time to thermalize. Okay, so you cannot apply notions of equilibrium simply because even if the dynamics would be perfectly well thermal with a temperature and everything, you wouldn't simply have the time to have equilibrated. So this takes us to glassy dynamics, because this is exactly what happens with glasses. Glasses are systems that do not have the time to thermalize. So quickly, let me give you a very brief review and very personal review of glasses. So take a ruler, as I was saying today at midday, take a ruler, a plastic ruler, and compress it, and look at the compression, the length of compression. What you get is that at the beginning, the compression is rather fast, then it gets to a plateau, and then slowly it saturates. I have completed this curve because the experimental curves we have concern this piece, so that you get the context. Now I'm going to show you in detail what happens here. So what happens here is that if the ruler is 0.03 days old, it makes this curve, the one I showed you previously, but with all this rapid speed. If the ruler is 0.1 days old meaning the moment you prepared it, no? You got the molten plastic, put it on the, etc. And you get this. And this has been done up to 1,000 days. But I know experiments where they go to 30 years instead of 3. And the time it takes for this to creep, we call this part creep to the final situation, it's linearly proportional to the age it has. So this is already telling you that something is happening in the ruler after a day, after 10 days, and it's nothing chemical, it's just some rearrangement of the molecules in the polymers in this case, but any glass will do the same. So it's telling you that you're never in equilibrium, and that you have slow motion, you have a rapid motion, which is always essentially the same. This is vibrations typically, and flexibility. Everything you try with your hands with a ruler will happen very quickly, and so it will not suffer the effect of time. But this slow motion, which has to do with the rearrangements inside the ruler, is extremely slow. And this has been checked with all sorts of glasses for all sorts of time scales. So this is already telling you that something is happening inside. So this is, for example, a colloidal glass. This is from Daniel Bohn in Amsterdam. A colloidal glass that is evolving, and you see nothing much seems to be happening. I mean, this is disordered, and this is disordered. What you see is a correlation that the rapid vibrations, which are quick, and then you see that the system decorrelates, but very slowly. So this is a slow motion of all these molecules. But you don't see much, and not much happens to the energy in the process. So this rearrangement is not you're not gaining a lot. You are going down in energy, but very, very, very slowly. But the rearrangement is considerable. The whole thing rearranges, when you look at the photos of these two, they don't seem very similar, because every particle has moved quite a lot. So you get rearrangements, but the ruler is still a ruler, and it hasn't changed dramatically. And this is typical of glasses. So if you were a biologist, you would call this neutral evolution. You would say the system evolves in a neutral way. It's doing a lot of reshuffling, but most of this reshuffling is not giving you an improvement in this case, energy, which is your variable that you want to optimize. Sorry? You're going a little bit down, and now I'm going to try to explain why there is so much reshuffling for so little gain. This is what you're, yeah, good. Another thing you see is what, if you were a biologist, you would call divergence. If this can only unfortunately be done in the computer, take one, make it evolve, now clone it into, of course this you can only do it in the computer, and make them evolve, and you would see that very soon these two diverge into very different configurations. So evolution will tend to separate, instead of, you know, everything converging to something, which is what you expect in equilibrium. On the contrary, this evolution is slow, but it sort of drifts away one copy from the other. Of course, you cannot have copies in real life. No?
What metric for people?
You can do some correlation, like the cosine of k times the d. They don't go very far, but they go as far as one diameter, which is as good as infinity. So the whole thing just loses its memory very quickly. This you would call divergence, and by analogy, so two things: evolution of glasses is essentially neutral. I mean, it is improving a little bit, but very little, and it has this divergence, of course, which you cannot measure experimentally because you cannot duplicate a system. So usually the explanation for this is to say, well, the landscape is essentially like a golf course. You are falling into different states, and whenever you emerge from one, you could go to any of your neighbors, and because you can go to any of your neighbors, you don't improve a lot, because each time you lose everything and you have to restart again from scratch. This is one way to put it. Another way which I like, by the way, inside a state, inside this basin, the motion is just the ordinary motion of equilibrium. It's not interesting, but it's the one that contains the phonons, the vibrations, the rapid motions, etc. But the slow motion, which has to do with changing basin, it's sort of not very, very slow to get you some improvement. So, in fact, if you want to really have a better look at this and a better understanding, you have to try to picture how you walk in infinite dimensions. This is a bit harder in a 2D picture, but basic idea is you have a basin of attraction and you want to minimize your energy, you want to go there. So your basin of attraction is a kind of area, a region in many dimensions. And one thing you know, and the boundary of this basin of attraction is the points that are undecided whether to go here or to go to another neighboring basin of attraction. You have many possible states to go. Now, you know that in high dimensions, a sphere in high dimension has almost everything on its crust. This is a property of the Jacobian, if you want, the r to the d minus 1, but this is typical of high dimensions. So typically, you're going to be near the surface of this basin, but the surface is precisely where you're undecided, because you're very close geometrically to the neighboring basin. So you are on the surface. Next step is that now you're on the surface, but the surface in itself is divided into sub-basins, because the surface in itself, if you are on the surface, you stay forever, and within it you have points of attraction within this surface. But the surface itself is high dimensional, it only has one dimension less. So that's now you're not only on the border between two basins, but now you're on the border between the border of the border. And this you can go on for not many times, but you can repeat a number of times, and you conclude that in many dimensions you're always undecided. And this is a peculiarity of trying to find your way in, and this is the main reason why the dynamics is neutral and why there is spatiation. When you are you're trying to get to the bottom of a well because you want to be as deep as possible in many dimensions, most of your time will be spent undecided whether you're going to the right or to the left. And this happens at many levels, and it's very, very, very general. In fact, if you're not convinced, you can analyze ferromagnetic coarsening in this way, and you will understand that it's this way, but let's go fast. Okay, so slowness comes from indecisiveness, mainly, and this is a property of anything that is trying to optimize in many dimensions. Many dimensions, I'm talking of phase space. Okay, so now we do a model that is simple. You just like the model that was done before for fitness. Now we're going to do it for glasses. We propose a number of states, and now we propose that we're going to choose at random a state anywhere else and accept it with the Monte Carlo rule, just the rule we wrote before. If you're going down, you accept. You're improving in energy, you accept. If you're going in the wrong direction, you accept with exponential probability. But now, notice what happens. When you choose at random, this is an exponential distribution of states. So if I am here and I want to go down, notice that I'm choosing randomly, but when you have an exponential, almost everything you have underneath where you are is just beside where you are. This is a property of exponentials. Exponentials grow so fast that almost everything is near just beside where you are, because these are exponentially rarer. So if you are choosing at random things that will improve your situation, and the number is decreasing exponentially, you typically are going to improve by very little. You're going to choose something that is immediately just a little bit better. Yes. Let us assume for a moment it is very low, yes. So imagine you always accept everything that goes down. Even so, you will go down extremely slowly, simply because you're choosing at random, and something that, you know, decreases exponentially, it's very hard that by just chance you're going to choose something that is very deep. So again, neutral evolution, you can see it also in this sense, that you go down by very little, just because of the number of things you have. And let me call effective temperature, it's not, this was done in the paper that I mentioned before by Maria and Boris Schreiman and Marc Mezard. The effective temperature is simply the log of the derivative of the log of the number of states. And it's what thermodynamically would be like an effective temperature, so, like a temperature. So this, you go down, and if your external temperature is sufficiently low, you will go down up to the freezing point. The freezing point is the point below which there are no states at all. But of course, you can see this as an adiabatic cooling. This is just what you would get with a system that is cooling adiabatically until it gets to its lowest temperature. So this is all in all the zeroth order picture of what a glass is. A glass is something that has rapid degrees of freedom that are not particularly interesting, and it has slow degrees of freedom that are like very hot, starting from the transition temperature, and they are cooling down very slowly until they finally reach the room temperature, or its own fast degrees of freedom. So this is the order 0, if you want, model of glass. I'm showing you this tiny toy model, but there are more sophisticated models where you don't assume this and you get it. It sort of happens. So that's already one thing. But now you could ask, well, is this as complicated as it can get? And now I need to introduce a further complication. Let me couple two of these systems. So I'm going to couple two of these systems constructed in the same way, but with different widths of distribution. So they are different. They have different effective temperatures. And now two things can happen. If I couple them strongly, but with any coupling, the two effective temperatures very quickly get to be the same. It's easy to prove. And so the system goes to the red lines where the two gradients are the same, and then they continue happily ever after, exactly keeping the same temperature. So now you have two glasses. I told you that a glass is something whose slow degrees of freedom are cooling down adiabatically. Now these two are cooling down adiabatically together. Well, this is all very reassuring. This is what you would expect of an effective temperature. But there is something much stranger that can happen if the interaction is weak but still there. What happens is something very strange. Because these two temperatures want to get the same, these two gradients, this system moves a little bit higher than what it should be, this a little bit lower. So this one acts as if it would have been more advanced in its evolution, and this one more retarded. And all in all, what happens is something that is very anti-intuitive, and it took us years to understand, that when you couple two glasses, if they don't manage to put their effective temperatures together in pace with one another, what happens is that the one that has the hotter effective temperature begins to move much slower than the one that has the highest. So you can still have two effective temperatures, but the time scales of motion of one and the other become more and more separated. So you have one that moves much faster than the other, and still both are moving much faster than the rapid degrees of freedom. So now we get really what is the most complex situation, and what, at least at the level of mean field, is the solution for all glassy models, is that you have many time scales nested one inside the other, so one much slower than the other, much slower than the other, much slower, and within each time scale you have a different effective temperature. Two things that are moving at the same speed have the same effective temperature, but two things might have different effective temperatures if they are moving at very widely separated speeds. And this turns out is the analytic solution for any mean field model of glass, much more microscopic than the one that I'm giving you here. Okay, so now back to fitness. Now, remember the two criticisms I did for the problem of fitness evolution. One was that the whole thing was only true if time scale separation allows for complete clustering into one type. Remember this. But now we have something that we know. If this evolution is an evolution in a glassy landscape, we said it already. You have the rapid evolution, which has to do with sound waves within a state, and then you have this very slow motion between states. So now time scale separation is given to you, and this is what you needed in order to have clustering. I'm going to come back to this. Number two was, even if I had detailed balance, even if I had a true dynamics that was thermal, I didn't have the time to equilibrate anyway. Well, true, but this is true about glasses, and so what you have to compare is not to equilibrium statistical mechanics, you have to compare to a glass that is in contact with a thermal bath, which has its own rules, and one of its own rules is this existence of time scales with different effective temperatures. Okay, so you gain and you lose, because you gain on the one hand because we are going to be able to really establish an honest and probably very general relation between fitness evolution and thermodynamics, but the price we will pay is that it's not going to be equilibrium thermodynamics, it's going to be glassy dynamics. So why do I say that timescale separation does the job? Because imagine you had this is the fitness landscape, this is just a sketch, and you had a region that has a very high fitness and another region that has a high fitness, and you're diffusing. So when you're here, you make lots of kids. If one of the birds goes here, it makes a lot of kids. And here, there is no clustering. You can have children that are anywhere in here, so you don't have everybody clustered into one. And here, the same. But if there is a timescale separation between this fast motion and this rare motion from going from one to the other, then I can just take the average fitness in here, the average fitness in here, and consider not the rapid motion inside, but the motion between islands, let's say, as something that will satisfy detailed balance. So this is what timescale separation does for you. What was an assumption that is almost never true, now it's true, provided you average away the rapid motion inside a basin. Okay, so now how do you model this? Well, imagine you want to model all this. This is a network of gene interactions. Very quickly, I just imagine that there are, many alternative paths, and they are, on the other hand, paths that have to be followed one after the other. So you could think of this as, there are ores and ants, and if I am very crude, fortunately I'm not a biologist, so I'm not responsible for what I say, you could, let's say, think the person who initiated this is Kaufman, who did things in the 80s, but I like better this model. You do some Boolean function, you have ores, and you have ants. These are genes that are expressed or not. For example, you have something that has to not be expressed, and so on and so forth. And this is a standard problem in computer science. It gives you a landscape that is glassy, just like the one I mentioned before, just like so this gives you a microscopic model, and if you define fitness as this, the log of the fitness, because these are many ands, as this energy, the number of errors in these clauses, then this is a rugged landscape, just like the one I drew with a golf course, in the space of these Boolean variables, which would be something that would be representing your genome. So this would be a way, much in the spirit of Kaufman, to do the modelization. But what I want to stress is that if I solve exactly this model, its dynamics, it corresponds to the system with many timescales and many nested, many effective temperatures and many timescales. We know how to solve the usual dynamics of this model and the usual thermal dynamics of this model, and it's a glass, and we know everything about it, and we know how it works, and we know that it has all these timescale separations. This is more microscopic if you want. And well, here I am simulating it. So what we do here is we want to promote this to a system where a genome is, you have individuals with their own genome, which is given by a number of spins in my language, and the fitness is given by this formula, and then these M individuals mutate, meaning that the spins flip, and then there is timescale separation. So now this timescale separation happens automatically, and I can try to do, now I can do this mapping to thermal dynamics because the argument of this clustering works, except that of course within a state you have to average the rapid mutations. Okay, so what does this mean? It means, for example, that you're going to have, in the case you have one effective temperature, you're going to have that two sub-strings are going to be, you can treat them as two evolving subsystems, just like I did a while ago. So if the coupling is strong between two substrings, what you're going to get is that they have to be thermalized and they have to have the same effective temperature. So this already is giving you relations between substrings of a long string that is evolving according to this rule. So this is a law that is sort of quite robust, and it's something thanks to this form of evolution that you're getting. No, in this case, I am actually putting it by hand. But if I had done a microscopic model, the interactions exist by the assumption of the model. The fact that you need to be, if you have two parts of your body, both have to be fit if you want to survive. You cannot just carry on with use some part that is not working at all. So this is a usual assumption that is done. But any interaction you put will sort of imply this form of thermalization. Time-dependent thermalization, because the whole thing is cooling down at the same time. It's not really equilibrium, but it's a kind of an adiabatic cooling. Okay, and now you have an effective M, which is, remember that the size of the system was working as if it were a temperature. And in fact, the effective temperature I mentioned many times, which is the derivative of the log of the number of states you have, in fact gives you an effective size. And what is nice is that this effective size is the size below which, if something is smaller than that size, your mutation rate is too bad and your system is going to corrupt, and the mutations will stop evolution. And this automatically tells you that the evolutions that were longer in creating and that are slower in transforming have the highest effective temperature and are the most robust to this mechanism, to a population bottleneck. And this was unexpected, and it's quite generic. So at least you can get some conclusions from all this kind of argument. So one last thing, and I think I'm done. Remember that the population size was playing the role of inverse temperature. So let me show you some experiments in spin glasses, so nothing to do. You cool them, but on your way, this is the AC susceptibility. So think of it as a measure of the fluctuations of the system. It's just a measure of how easily the system responds to a kick in any direction. So you cool it, and then you stop here, and because you stop this out of equilibrium, this susceptibility goes down. This is normal, and then you continue to move. It goes up and it goes this way. That's okay. That's not very special. What is special is if now you heat it at uniform speed and you retrace, the system retraces its steps, and this dip that you created when you were going, suddenly the system remembers that it had a dip, and it sort of retraces the dip. And you can do two dips and it retraces both dips. And this is extremely surprising. It has to do with things that happen when you waited here. You sort of imprinted, you made some changes in what was changeable at that time scale. And then when you went down, you forgot completely of everything. But when you go up, even if you go fast, when you go through the same temperature, you find this, this dip. This is an extremely, well, of course, there are papers trying to explain this. Now, what I'm saying is that if anything of what I'm saying here is relevant, we should be able to do the same experiments starting with a small population. Remember the M population number was 1 over the temperature. So we start with small, large temperature. We let the system grow. Then in our chemostat, we stop at a certain small population, we measure some characteristic of the system and then keep on growing, and then we go back, and the idea would be that when the population reaches the size where at the same size we had stopped a while, something should happen. I mean, some dip in some characteristic, some memory should be left of that. I don't know if this is the case, but it seems like a logical transplantation of ideas from glasses if this analogy holds. So I think that at the very least is an interesting thing to try. So I think I'd better stop here. I just wanted to say that putting two fields in contact is always fun. You can try to learn things. The big dream of mapping evolution into equilibrium stat mech, unfortunately, is asking too much. So that was the original, and that's probably why people didn't massively jump onto this. But if you set yourself the much more modest task of mapping a system that is evolving into a system that is out of equilibrium but performing glassy dynamics, slow aging dynamics, then this sounds like a much more probable scenario, and very close to be true, very probably. So thank you very much.